So very quickly to introduce our four speakers for today, we have Natalia Ares, Zhenyu Cai, Dominic O'Brien and Sarah Thomas. And these are four fantastic researchers who are leading our activities in engineering in the field of quantum. We have Natalia working on artificial intelligence and quantum technologies, Zhenyu working on quantum error correction and quantum error mitigation, Dominic on optical communications, optical wireless communications, and Sarah on devices for quantum networks. And we span a broad space and integrate really well with the rest of the university's activities in quantum, and I'm delighted that we've got all four of them here tonight. So I think, who's going first? You first, Dominic, so I'll hand over to you.
Right. If I can work the technology, first of all. There we go. So, yes, I'm Dominic O'Brien. I celebrated my 30th year in the department about 10 days ago. So I'm going to spend... Most of the time it was something you would applaud about, you know, everything has their low and high moments. Right, so quantum technology is something the UK is really good at. Back in 2014, the government made some investments to start a UK's national quantum technologies programme. That now, some decade on, after some renewed twice really, consists of 5 research-led academic hubs, about 15 to 20 universities in each hub, covering many things of interest in quantum technology. So there's one in quantum networks, so that's taking, if you like, the future quantum internet, you'll hear about a bit later. There's one in biomedical sensing, so some things you could do in quantum will be good for biomedicine. Position, navigation, and timing. This is all about removing our reliance on GPS using quantum devices. Sensing, imaging, and timing. You can sense gravity to a very high degree of precision with quantum technologies, much better than you can do otherwise. And actually the one that I'm involved with, I'm actually happy enough to be the director of it, which is quantum computing, and that's led by the University of Oxford. But it's very much a partnership. So we've done that for a decade, and just to show you what I think a successful research program looks like of scale. So the quantum computing hubs we started back in 2014. That was led by somebody called Ian Walmsley by Oxford University in the physics department. We kind of morphed 5 years later into the QCS hub, which I directed, and then 24 to 29, I'm directing the one that's QCI3. But what do these things do? So, of course, we're academic researchers, so 1,000 publications across those hubs in the topics of quantum computing, spanning everything from hardware to software, very broad. We built partnerships, 60 additional projects with industry, with academia, quantum computing for music composition, would you believe? A very broad range of diverse interests, patents, spin-outs. And those spin-outs are really, the quantum computing spin-outs form actually a real core of what's quite a burgeoning industry in the UK now. And that 230 should almost have a 1 in front of it, because one of the spin-outs was sold for over $1 billion. It's kind of number 2 in the pantheon of how much Oxford made from its spin-outs. Number 1 is an engineering company. This is number 2, but it was sold for $1 billion. Only 6 years old as a company. So quantum computing is a really exciting place to be. So this is quantum at Oxford. This is something, you'll never read everything here. The only point of this slide is to show you something that Oxford is really globally one of the centres of this stuff. Not just where we sit in engineering. In fact, we're latecomers to the game. Of course, there's a vast amount in physics, in chemistry. There's work in philosophy on the foundations of quantum. So it's a very, very broad range of things. We now have a director of our Oxford Quantum Institute, and engineering works closely within that quantum institute. The darker bit is what we do in engineering science. So this is what you're going to hear a little bit about this evening. So don't even try and read the text on that. It's a bit small to read. So that's a bit about what's going on in all of Oxford in this area. Why is it interesting? So Quantum 1.0 has been around for some while. So really, things like the microprocessor from the early Intel in the 1970s up to the 16 billion transistors in your Apple at the moment, are all about being able to control atoms, but large numbers of atoms. But we can control them very, very well in semiconductors. Things like the white LED, for instance, that's gallium nitride, again, because we can understand the quantum properties of large numbers of things. We've known about that since the 70s, really, and just got better at it. What's really changed is being able to control the properties of very small numbers of species, so single atoms or single ions. So that's actually a real video of a single calcium ion from my colleague in physics, and that's held and controlled within an ion trap. And two of the states of that can form things called qubits. So the bit at the top is called a 1, bit at the bottom is called a 0. We know about bits. The interesting thing about a qubit is it can exist in both states at once. Why is that important? For a quantum computer, that superposition, that being both things at once, allows you this kind of simultaneous computing of both possibilities. So you don't have to try the 1 and then try the 0. You can do them both at the same time in your quantum computer. That's kind of part 1. Part 2 is entanglement. So Einstein called it spooky action at a distance. And you can lock together two electrons or two quantum objects and then move them apart, and they're locked together. It's not like there's one of one. They're intrinsically one thing. And in a quantum computer, that provides the wiring between the qubits. It allows you to build big numbers of qubits up. That's all I'm going to talk about. I'll leave the experts who follow me to talk a bit more about this stuff. But those are the two things that we're trying to harness in Quantum 2.0. So for computing, why is that important? The power of a quantum machine scales exponentially with the number of qubits. So if you add one more qubit, you double the power of the machine. There are problems where the difficulty scales in the same way. Classic one is the traveling salesperson problem. The route between various sites scales very quickly as the number of sites scale. There's other things, other than logistics, things like chemistry, drug discovery. All I'm going to say about this is, of course, it's an enormous field. Where are we in its development? By about 2030, quantum computing will probably have developed to the point you can use a machine to gain what they call narrow advantage. That means that you can do better for very narrow specific tasks than you could use using a conventional machine. By the mid-2030s, all of the predictions, all the roadmaps tend to say about large-scale useful machines. So this stuff is coming over the next decade or so. We'll see a real change, I think. And you'll hear some of the enabling stuff in the later talks this evening. The other thing you can do with quantum is quantum communicate. And I'll go into a bit more detail about this because this is work I actually do. This quantum state, this thing, you can't copy it without somebody telling that you've copied it. So you can't make an ideal copy. Somebody will know. So you can detect eavesdropping. If I send one of these things over there and somebody intercepts it but makes a copy so nobody knows, they'll be able to tell. So that's the sort of principle. That's quite developed. So I'm not going to go into the detail. It's called prepare and measure. That stuff is commercialized. So you can buy QKD links. I'll show you some pictures in a second. But the problem with those is they rely on, you can have a link which is secure, but when you get to the building, you need to have locked it up really well because actually it's only secure to the end of the link. And if you need to go 2 hops, you need to trust the person who owns the terminals. So that's the problem. And you'll see from Sarah's talk after me, the sort of next generation is actually distributing this mysterious stuff called entanglement. And that means you don't need to have some trusted nodes. So that's what's going on at the moment. The UK has quite a big program doing that. Just a bit more about the scale of that and why is it interesting? Well, for satellites, people are interested in sending secure information globally. So popping up to satellites and the satellites all orbiting around, that's quite a big area of interest. The UK, in fact, these are pictures from the UK's quantum satellite that's going to be launched next February. And the ground station that sends actually receives a single photon from space. It's pretty amazing that actually it doesn't receive it very often. You send quite a lot and they don't get there, but that's the nature of loss. There's also a fibre network in the UK. You can see it runs from out in Cambridge down to Bristol via special fibres. So you can do secure, provably secure communications across the UK. And the stuff I'm going to show you very briefly, we've been doing this sort of handheld to handheld devices over about a metre. So your smartphone could communicate with another smartphone securely, not using radio. And this just shows you a picture of where we got to. This is work we did some years ago when Nokia actually made stuff. And they don't do phones anymore, they did then. And this is a handheld link. So you see the hand, these are the links on the right-hand side. And what it's doing is sending a beam of photons from there to there and securely communicating. I thought I should show you a picture of real engineering because actually a lot of it's about the nitty-gritty of how it's all assembled and how it all gets put together rather than necessarily anything. The quantum magic goes away quite quickly. Then reality hits when you have to make the link work, as you might imagine. In my final slide, this is more recent work we've been doing. So if you wanted to secure wireless communications with quantum, you need to use light to do that in a room like this. So this is our test room. So up in that ceiling, there are a couple of terminals that fire beams of light to these things sitting on a trolley. It's kind of early days for this stuff. But the interesting thing is we did wireless, so we did 1.6 terabits per second. So that's a fairly quick wireless link, plus some quantum stuff with one of our collaborators to show that you could combine this quantum and classical security. Now with that, I'm going to leave it because that's my last slide. I'm going to hand over via Clive to Sarah, or I'm going to hand it over to Sarah Thomas, who's going to talk about where this stuff's going to go in the future. I'll put up a slide, and we're going to do questions at the end. Right, thank you.
Okay. Hello, everyone. So, sorry. Good. So I'm very new in the department. So Dominic said he's just been here for 30 years. I've actually just started this year, so I'm one of the newest academics. So I'm going to talk just a little bit about the kind of research I'm going in the direction of, which is building what we call quantum networks, or sometimes people are starting to call the quantum internet, or what the future of the internet would look like. So a lot of people in this field, when you think about, okay, what might the future of quantum technologies look like, they perhaps have some kind of grand vision in mind, where you think about, okay, this is, I guess, a map of Europe, and it's showing these links in shining blue. And these would be these secure links of quantum communication. So these allow you to do this ultra-secure communication, even if somebody had a quantum computer, which would actually be able to undo a lot of the encryption that has been used for decades. So if you now encode your information using quantum states, you've got this kind of intrinsic, unbreakable security to send information between users. So that's the first step. But then what happens at kind of these nodes? What would the future of quantum tech look like maybe within a city? And perhaps you'd have some local quantum network. So you need to be able to communicate across the city, but also be able to perhaps remotely access a quantum computer. So there are lots of different ways that people are exploring to develop these computers with these really exciting potential to solve difficult problems. But it's, I'd say, very likely that you would never have a quantum computer in your home, right? It's incredibly likely, therefore, that they would be similar to a large data center where you would need to just access it remotely. So therefore, different users that have these problems they want to solve need a way to be able to send information securely to this quantum computer or this quantum data center. It's also looking increasingly likely that quantum computers themselves will probably be made up of some kind of smaller scale quantum network. So building these processing units, as we'll hear a little bit about in the next few talks, is really challenging. There's a lot of engineering challenges that goes into building these. And actually, it's likely that they will be made up of several smaller devices, which maybe contain maybe hundreds or thousands of qubits, and these then get also connected together in this way. And this is a scheme that's called distributed quantum computing. So not only would it perhaps be easier to make kind of several smaller processor units connected together, but there's also a lot of advantage, actually, of separating out each of these units. So they can be kind of more powerful together if you connect them than each one would be individually. Okay. So how do we build these kind of large-scale networks, and what are the resources that you need to do that? So the key resource that you need to build quantum networks or to connect quantum devices is actually entanglement. So this is this state of two or more particles that Dominic talked about that has a state that you cannot describe by each particle individually. You can only describe it together as the whole system. So let's say if you've got an individual quantum particle that can exist in either of these two states, 0 or 1, and let's suppose you can create a state that is either both particles in state 0 or both particles in state 1. What you cannot do, if this is your entire system, is describe the state of just one particle at a time. You can only describe it with the entire state. So these particles have this really, really strong intrinsic correlation that actually can't really be described, or kind of, there's nothing in the classical world that's quite as strong as the correlation between these two particles. And that is actually an incredibly useful resource that we can use. So the first thing that you can do, if you've got two users that share an entangled pair of particles, then if those users can make measurements on those particles, they can actually share quantum keys. And that can allow them to then have a secret key that they can use to encrypt and send information. And that, as Dominic said, that doesn't rely on any intermediate trusted nodes. If those two users share entanglement, they can essentially share that secret key or send information securely. Another thing that you can do is you can actually do a very kind of sounds like sci-fi thing, is you can do something that's called quantum teleportation, where you can use this pair of entangled particles, and you can use that. They get destroyed in the process, but you can use it to send information from one user to another. So it's not quite like you can vanish a person in one place and they magically appear in another place, but the information that was encoded in that particle, that really does get teleported from one place to another place by using entanglement as the resource to do that. And the final thing that you can do with entanglement is you can connect these quantum devices together. So on one of Dominic's slides, it said that entanglement is kind of the wiring between these different processors in a quantum computer. You can also use it to connect together different devices called quantum sensors. And by having quantum sensors that are entangled, that share this entanglement, they can have much higher precision than if you just had one sensor. So therefore, this is the kind of key thing that we want. If users across a large network have entanglement between them, then you can do all of these things. You can send information, you can send quantum states, and you can do distributed computing and communication. Okay. But then the challenge is, how do you get entanglement between two users? So let's say we can generate a pair of particles. We normally think of them as photons, which are particles of light, because those are then very easy to send long distances. But those particles are very fragile, and if they get lost, your entanglement gets lost. So how can you therefore get that entanglement over really long distances to build up large-scale networks? So let's say our two users are now really far apart, maybe hundreds, maybe thousands of kilometers. So what we can't do is generate these states and just send them hundreds of kilometers because they'd get lost. So you have to do something else instead. You have to think about, let's take that really long distance over which we want to have the entanglement and split it up into several smaller sections. Right? So maybe you're familiar when you send information classically, of course, loss is something that you also have to deal with. You have these things called repeaters, which basically amplify the signal every however many kilometers. We can't do that in quantum, right? We can't just amplify the signal because that destroys the quantum information. So instead, we build something that's called a quantum repeater. So every maybe few kilometers, you basically have what's called a repeater station. So you split your link into these smaller distances over which you can share entanglement. Right? So if I now have entanglement between here and here, and also between here and here, what you can do is you can do a special measurement on these two, and given a particular outcome of that measurement, you end up with entanglement on the outer two. So therefore, you've extended the distance over which you have entanglement. And if you do this enough times, you can sequentially basically extend the distance. And that's what we need to do over these large-scale quantum networks. So this is one way that you might think about building this concept that's called a quantum repeater, which the goal is to end up with entanglement right between the two far ends. So we always call them Alice and Bob. And we do that by splitting it, as I say, into several smaller sections, and then sequentially doing these measurements to make the distances bigger and bigger. There are several key hardware devices that we need to be able to do this. The first hardware device is you need a way to generate these pairs of entangled particles. So we deal with light. Light, of course, travels at the speed of light, and therefore it's the only really viable way to kind of send information over long distances. So you need a way to generate these pairs of particles of light that are entangled with each other. And then you also need a separate device that's called a memory, a quantum memory, that can store that information for some time. And the reason that you need this is because every single part of this scheme only succeeds some of the time. It's probabilistic. So if you don't have these memory devices, then the whole kind of overall scheme would fail, right? But you use the memories to keep hold of the successful events until everything else has succeeded, and gradually you can do this over very long distances. So therefore, to build these quantum repeaters, which are key for long-distance quantum networking, we've got these two key hardware devices. Firstly, sources of entangled pairs of photons, and also quantum memories, which are devices that basically allow you to store quantum states of light for some time. There are lots of different ways to do this. I'm going to talk about just the ways that I work on in my lab, but there are many others. So just very briefly, one way that you can generate pairs of entangled photons is by using a device that's called a quantum dot. So a quantum dot is a nanoscale semiconductor of one particular semiconductor species that's embedded in a different semiconductor that has a different band gap. And what this leads to is a system that is very, very confined and therefore has these very discrete energy levels. And you can actually use this if you excite it. It generates this electron and this hole within that nanoscale semiconductor, and it will emit a photon, just one photon. And it does so incredibly efficiently, in particular if you put it inside a cavity. But you can also engineer it so that instead of just giving you one photon, it will give you two at a time. And they always have this property that either they both have one particular polarization or they both have the other polarization. So that's exactly what we want. They come out as pairs that are entangled in their polarization. The other device that we have is this device that's called a quantum memory. So this is some device that allows you to take light and keep hold of it for some time, right? And this allows you to synchronize the probabilistic sharing of entanglement. And typically these are developed by using some kind of interaction between atoms and light. So atoms will absorb light, and therefore if you engineer it in a particular way, you can get it to controllably absorb and then re-emit the light after a certain time. So just to show you a picture of some kind of real devices that I'm building, this isn't my new lab, because my new lab is still very, very empty. This is my previous lab. But this is what some of these devices might look like. So this here is this is a cryostat that cools down to around 4 Kelvin. And inside here is a little semiconductor chip that has these quantum dots. And we can excite this, and then it will emit single or entangled photons. This is a glass cell that has some atoms inside. And you can see that if you send lasers through it, the atoms will actually absorb light and then re-emit it. So what you can see is some fluorescence. So this is some controlled absorption and emission of light using an atomic ensemble. And this is just an example of how these experiments look like. So you can see it's very, for now, kind of quite large-scale bulk optics experiments, as we're in quite early stages of kind of developing some of these devices. Great. So yeah, I've showed you a little bit what maybe the future of quantum networking will look like, and some of the hardware devices that we're developing towards that. So yeah, thank you very much.
Okay. Thank you, Sarah, for the very nice introduction to quantum internet, and also for Dominic for the good overall introduction of the quantum technology side of the department. So I'm Zhenyu Cai, and I'm going to tell you about cutting through noise in the quantum age, which is a very vague title, so you have no idea what this is about. And so you heard a lot from Dominic about all of the great potential that quantum computer has on kind of like drug discovery and optimization and material simulation and things like that. And you must wonder to yourself, where is my quantum computer yet if it can do such a great thing, right? Why isn't it kind of like somewhere in the cloud that we can access and try things out and things like that. And the fundamental reason, the most major roadblock towards that is because of errors. Errors in the machine, noise in the machine, because of unwanted interaction with the surrounding, because quantum systems are just such a fragile things, microscopic scale. And then also because of the imperfect control that we kind of, when we try to operate them, because we try to compute. Because we don't want a computer that's really, really fast, but get it wrong every single time, right? Yeah, that would be no good. So to give you some kind of perspective, for commercial RAM in your laptop, in your phone and things like that, their lifetime is typically centuries on average, so each bit will last on average centuries before it's corrupted. It's of course not to say that your phone will last centuries, because it has billions of transistors inside nowadays. But if you look at quantum bits, qubits, built out of like silicon spins or trap ions or like superconducting qubits and things like that, then all of these qubits, they actually only last microseconds to minutes, their lifetime, before they're corrupted. So actually there is orders of magnitude difference between these two types of things, even though their names are very similar. And it begs the question of how can we actually build a reliable machine out of all of these very, very fragile components. And this is kind of where the meat of my research is about. So the first type of things that people try is what they call quantum error correction, which is error correction with the word quantum in front of it. This is not very informative, but we do draw our inspiration from classical error correction, which the basic idea is just you're given a bit. What you can do is you can copy it to 3 bits, for example, and then if there is an error happen, you can kind of like perform checks or whether the first and 2 bits are the same and whether the second and third bits are the same, and then you can detect the error and correct it and restore your information. So I will not go into details about quantum error correction, but the principle is quite similar. So you try to distribute your information in 1 qubit into multiple qubits across many, many qubits, and then you perform checks on subsets of qubits to detect this error and then recover your information. There are a bunch of caveats that you need to deal with when you go from classical to quantum. For example, there's the no cloning thing that Dominic has mentioned, and then there is also, it's very hard to just like measure error on the quantum system without disturbing them and kind of like, without kind of like collapsing them, destroying their quantum property and so on and so forth. But the overall principle is very similar. So you distribute information across multiple things, and then you perform checks to deal with errors. And so this is quantum error correction, and there is another different ways to deal with it. This is called quantum error mitigation. And what it is let's say we have a quantum circuit, so qubits with gates apply on it, but all of these gates and all of these qubits, they suffer from noise, suffer from errors. We don't kind of try to remove noise in these qubits and gates, so to speak, but we actually run a different configuration of this noisy circuit, an informed kind of like different configuration, and then another different configuration of this circuit. And via this different configuration of circuit, we'll try to probe what is the effect of noise on our circuit output. So we probe the kind of damages that this noise is doing to our circuit by running different configuration of it. And then based on this information, we'll try to recombine all of this output in an informed way, such that all of these different damages, so to speak, they cancel out each other and give us a kind of like error mitigated output or noiseless output, so to speak, which is quite similar to the way that the kind of classical signal processing is doing. And so with these 2 different disciplines of trying to deal with noise, they each have their own advantage and disadvantage. So the advantage of quantum error correction is it offers very, very strong noise suppression, and then it also do not require additional number of circuit runs. And the advantage of quantum error mitigation, on the other hand, is you don't distribute your information across multiple qubits, so you save on qubits, and also you have much lower hardware requirement because you don't perform error checks and things like that. So the kind of research that we do in my research group is basically try to devise normal protocol of quantum error correction and error mitigation for quantum computation, and we are actually one of the pioneers in quantum error mitigation. And we'll try to also kind of like develop integrated framework that try to combine quantum error mitigation and correction in a kind of like beyond naive, one on top of another way, some kind of like native integration. And we also kind of try to look for other noise control technique. For example, try to tailor the noise to different situations, try to change the form of the noise, try to go down to the device level and study their pulse control and stuff like that. So this is the kind of like cutting through noise that I mentioned in the beginning that we do about. So all of this seems quite abstract theory and not very engineering for tonight's talk. And you might think that, okay, while Dominic and Sarah give very, very nice picture of their lab, you would think my lab look kind of like this. Well, it's not very far from truth, besides you need like a few more cups of coffees and stuff like that. And we do actually collaborate very, very closely with our hardware colleague, because noise itself intrinsically arise from the hardware themselves, so we need very close integration between the quantum error correction and mitigation technique with the hardware itself. We collaborate closely with Quantum Motion, which is a silicon spin qubit startup company in London that I'm affiliated with. And then also the Oxford Trapped Ion Group, which just set the world record in the qubit fidelity they can achieve. And many more collaborators around the world. And we, in collaboration with them, we do design a lot of different architectures for implementation of this quantum error correction and mitigation scheme down to the device level. So it's not just like abstract qubit and things like that. We do try to lay things out and actually see how things can be actually built in practice. And such an integration of hardware and also this quantum error mitigation and correction scheme has become more and more important with the recent advances of the various hardware platforms across the world. And two very prominent examples is, for example, this Google experiment that demonstrates the validity of quantum error correction using 101 qubits just late last year. And also this experiment from IBM that demonstrate the validity of quantum error mitigation using 127 qubits, showing some showing some simulation result that no classical computer can efficiently simulate. So these are all very exciting time, and more such results will come out as we build better and better quantum computing platform. And eventually, with all of this come together, quantum error correction, quantum error mitigation, and then all of this hardware integration and also tailoring towards the application side of things, will move closer and closer to the promising land of quantum advantage of material discovery, optimization, and chemistry that Dominic had mentioned about. And hopefully, we'll get there sooner than later. So with that, I'll hand it over to Natalia, who is going to tell you a bit part about potential way to achieve this success, which is AI in quantum.
Hello, hi. My name is Natalia Ares. I hope you still have a bit of energy for me. And I'm going to tell you about the intersection of two big fields. One is quantum, and the other, another rapidly evolving field, which is super exciting, which is AI. Now, AI, the intersection between AI and quantum can have different questions answered. And one is, what can AI do for us, helping us build these technologies? That's AI for quantum. Another question that you can ask yourself is, okay, if I had a quantum computer, would that help me run more efficiently or more powerful AI algorithms? And there are all sorts of bridges between quantum and AI that we can think of. And I'm going to tell you our progress in AI for quantum. And because this is Engineering the Future talk, I'm also going to tell you a bit what it's exciting going towards these bridges between quantum and AI. Okay? Good. So you heard a bit about these quantum devices. And I can say that one of the questions is why do we need AI to control them? And already you know that these devices need very precise control because they are prone to errors and they need to be controlled very precisely. Now, one could say that controlling a drone and a quantum computer bear some resemblance, and you would say that that is a bit of a far-fetched analogy. But we have a paper in which an approach in AI is validated by flying a drone and controlling a quantum device. So it's here, it does. So this is a very powerful tool that we can use to help us build these computers. Now you heard a bit about this already. In a classical beat, we have zeros and ones, and we do those with classical chips, and we have basically gate voltages that allow us to turn them on and off, and that's okay in terms of control, fairly okay. But for the quantum bits, where we have zeros and ones and possibilities populating an entire sphere, that's a bit more complicated. Also because the environment has a big effect on quantum states, and it's prone then to errors. So it's a very difficult control problem that we need to solve here. And in particular, following this analogy and this example of semiconductor devices, I'm going to focus today on semiconductor devices that are controlled electrically. We can use this for quantum computation. And you can see here an example of those semiconductor devices, electrically controlled. You can see that we are very excited about the potential of this technology for scalability because based on the success of CMOS technology, we know that we can pack lots of these devices in semiconductor chips. And you can see here Intel, these are quantum transistors, let's say, and how many of those we can pack in 300 nanometers. And these are the kind of devices that we use in the lab. Of course, in order to reduce thermal fluctuations in these very small transistors and preserve quantum effects, we need to lower the temperature. We use dilution refrigerators that lower the temperature to 20 millikelvin. And this is a photo of a portion of our lab. And this is how these dilution refrigerators look in the inside. Probably you've seen those in the news. But how do we control our chips? So we send signals at low temperatures for control and readout. And these signals go to big PCB boards. And you can see the chip somewhere here, the little semiconductor chip. So this is not a quantum computer. This is the quantum computer. So now the question is, how do we actually control the signals that are required to encode the qubit? So now you can think again as a transistor, these devices with some inputs that are bias voltages and gate voltages, and there is a current flowing through this transistor. Only difference is that instead of a current, we would use single electrons that we isolate, and we will encode the qubit in those single electrons. Now, in order for these to operate as a qubit, there is a process. We first need to define the qubit, let's say confine those electrons so that they are isolated. Then we have to get them just right, and finding, operating, and readout configurations. But this is not such a, linear path. It's actually a decision tree that has feedback from measurements that we constantly take from the hardware. So this is a process that is extremely time-consuming, and it's a bottleneck to the scalability of these devices. So what can we do about this? Well, we need a tool, and that's where AI comes in. But how difficult is this problem? I can tell you that it's as difficult as finding a needle in a big haystack, 2 meters by 2 meters by 2 meters. And we at Oxford were the first to design an AI algorithm that allows us to find that needle completely automatically. So what you can see here is the first qubit that was done by was configured by an AI. And those are the gate voltages that has found as configurations that are possible. Now, of course, I zoomed in. If you were to zoom out the parameter space, you would see that it's just a tiny volume in a gigantic space. So this is fantastic, not only because we can go and take a coffee while this happens, but also because this is the pathway to actually scaling these to large semiconductor quantum circuits. And this is how we are going forward in terms of letting AI play with bigger and more complex circuits. How did we manage this? We have a big network of collaborations and companies with which we work very closely. In fact, we have our lab at Oxford that I showed, but also via the cloud, we control different experiments around the world. So this is because we test our algorithms in our own devices, but also in other labs, and so to make sure they are robust. And this has allowed us to design algorithms that are really enabling in terms of the next steps of this hardware. We also work a lot in collaboration between our colleagues, because now we are bringing together the most advanced techniques in machine learning and the most advanced techniques in the control of quantum devices. So to bring that together means we have to work quite a lot and quite closely. Now, what next? AI is fantastic, and it could be, and as I said, it might be that when we have these quantum computers, we can run more powerful AI. But already, we know that AI, it's great, but it's very energy intensive. We have these LLMs, that large language models that cost a lot to train, a lot of energy. But we know of some learning machines that are a lot more efficient and very powerful, right? So can it be that we can incorporate some elements of quantum that allow us to run these large language models, for example, a lot more efficiently? And this is something that we are exploring by replacing in the machine learning classical architecture some little quantum elements. And this we can do before we have universal quantum computers, just trying to explore which elements of quantum might give us an energetic advantage in this case. Okay, with that, I'd like to thank you very much for your attention. Thank you.